Welcome to Web Handling. My name is Dave Roysum. I am super excited to start a new series on troubleshooting some of the most difficult problems in the web industry, namely rare events. For purposes of illustration, we will focus mostly on web breaks here. However, many of the tools and techniques we will use will have much wider application for the industrial troubleshooter. I put web breaks and other rare events on my list of a half dozen run and hide type problems. What I mean by this is if the boss is looking for someone to be on the web break team, don't raise your hand. The challenges are most obvious because they are costly troubles. Breaks and other rare events may be a notable source of waste, delay, and customer complaint. However, these cost concerns are not the only troubles for the troubleshooter. For example, problems such as this are statistically rare. Now, I know that many of you are already thinking, no, breaks are not rare in my plant. We see them every day. Be patient, my friends. I will explain why even daily events can be statistically rare, and how that poses extreme challenges for the troubleshooter with regards to data gathering. The second challenge area for the troubleshooter is that there is no single root cause as such. There may not even be a single mechanism. However, no matter whether breaks are 1, 2, or 3 separate mechanisms in your plant, each mechanism will have a different set of several strong factors that need to be identified. Correctly identifying the specific mechanism is essential to get the correct remedy list. For example, the remedies for a web break caused by the edge of the web rubbing against something is quite different than the remedies for a web break caused by someone breaking a light curtain and sending the machine into automatic e-stop. It is good to begin with a super careful definition. Runnability is defined as the mean or average distance between defects or troubles, or, in this case, web breaks. This distance can be expressed in different ways, depending on what is most convenient. This distance could be length, such as meters or yards. It also could be time, such as hours or days. However, the paper industry commonly uses a basis of 100 rolls. Thus, a 2.5% break rate, such as might be seen on Brittle newsprint on their customers' printing presses, would be 2.5 breaks per 100 rolls. However, we need to qualify this definition. Some materials have more troubles than others. Hopefully, it is not your competitor that is giving the customer less troubles. Not only are some materials more prone to troubles, some machines running those same materials are more prone. Here, the performance difference may be striking and somewhat unpredictable. Sometimes it's the old machines that are poorly designed and poorly maintained that give the most trouble. Other times, it is the new machines that are more demanding in the sense that a break will cause more trouble on a high-speed line and thus is less tolerable. Sometimes it is just that some customers are better complainers than others. Finally, the operating conditions on the machine where the break or other troubles can happen greatly influence runnability. For the web break case specifically, that would include tension settings, drive stability, roller alignment, and other considerations. These are well covered in my paper, Combined Stresses in Webs Going Over Rollers, which shows you how to calculate a safety factor from all of those insults taken together. Materials are far more complicated than a single comparison of the runabilities between you and your competitor will ever reveal. Merely telling whose material is better by a single metric, such as runability, might require a sample size of thousands of rolls, as shown by Page and Seth. Even then, you would have absolutely no clue why your web performed more poorly. There are 1,000 ways your web is different, any of which, singly or in combination, might be largely responsible. Worse yet, we simply do not have the means to independently change just one property and not any of the others. Yes, we do have some ideas which properties might be more important for a given performance metric, and we will get to those in the next clip. However, these will be shown to be only lightly correlated to breaks at best. The reason is simple. Materials are only a fraction of the system. Finally, as shown by many authors, starting with Seth and Page, brittle web breaks are extremely sensitive to environmental conditions. Here, we are not referring to machine conditions, or operating conditions, or your material properties, but rather the environmental humidity at your customer's plant and their storage practices. Machines are no less daunting than materials. However, rather than make lists of why a specific machine property might matter, we can make our life a bit easier by letting the web tell us where in the machine it is not happy. In this way, we treat each span of the machine as a separate machine. In this down web break location histogram, we see lots of breaks starting on the unwind. If so, we might postulate that something about the unwind is brutal on the web. Perhaps the roll is out of round, or perhaps the layers have a bit of adhesion, or perhaps the tension control there is poor. Another working theory could be that the web might be so troubled that it gives up on the very first chance it has, and thus is not destined to make it through most any span of most any machine. On the other hand, a web break rate just before, at, or just after a process might indicate that that area is poorly maintained, or perhaps the process itself is brutal on the web. Once we know where the troubles start, we can now position the next tool in our Getting Started toolbox. That is, a camera to capture the event. For problems such as brittle web breaks, filming is essential because the event occurs way too fast for the eyes to see. Besides, who can stare at the web for hours at a time without blinking and then remember what they saw? Here we have two ways of capturing what is likely a very short duration, high-speed event. The cheapest, but most time-consuming, is to use something like an industrial-hardened security camera with circular recording. However, the area must be evenly flooded with light, and the camera must be able to perform well at high ISOs to get a fast shutter speed on the camera to freeze the action. Even then, You still may not capture the event on the first or second or even third try. The reason is that brittle web breaks may occur between frames. Still, with a bit of skill and patience, you will eventually see the web open up a tiny bit on something somewhere, and then you have caught the criminal in the act of the web break crime. A much surer but far more expensive route is to use high frame rate cameras. These are temporary setups and also require flooding the area with light, because they take footage at more than 1,000 frames a second. You will not miss a thing. A third option is emerging, and that is the tiny sports cameras that can capture video at 400 frames a second. A wide-angle lens and a large depth of field are very helpful also. It is essential to make every attempt to recover the sample where the rare event occurred. In the case of web breaks, you would try and find and save both sides of the entire width of the break when possible. I have seen winder operators dig into a mountain of paper bigger than an automobile and find the area of the break that started on that was no larger than a fingernail clipping. In at least 2 fiberglass web break troubleshooting cases I worked on, recovering the break sample was the primary or only way that the root cause mechanism was found. In one case, it was excessive in-plane bending caused by a spreader, and in another, it was due to core diameter variation on a set that caused the smaller core to miss on the automated turret transfer. A brittle web break has some tells on where the break started. True, as we will see in the next clip, 80% of all web breaks start on the edge for reasons having to do with mechanics. However, we need not make that assumption. The branches on the fractured surface, when present, point to where the break started. If you have lots of branches, such as with very brittle materials, you don't have to look over much of the break surface. With less fractured breaks, such as slightly more ductile materials, you will have to search a bit more of the surface, perhaps using a magnifying glass. Finally, with ductile materials, you will need to search the entire width of both halves of the break, but paying particular attention to the edges. The next step is to classify the mechanics of the location of the break initiation or other rare event. Shown here is the weak spot causes for web breaks in the case of newspaper, which is by far the best documented. In this graph are hundreds of breaks that were studied and classified. Note that with care and with this material, there are very few unknowns. Almost all breaks started on a location of contamination. Later work by paper mills and reported by FP Innovations, a Canadian research center, showed that the tiniest vibrations of a nip forming roller was the downweb location of break initiation. Now we can see why web breaks are statistically rare. They started on a spot smaller than your little fingernail. During that time between breaks, 1 trillion times as much unblemished and thus successful material passed. In the case of shives and forming roller vibration, 1 trillion areas of weakness passed without trouble before the web decided to break on the next one. In the last slide, we detailed the well-documented case of newspaper. There are other break initiation sites known for other materials. For example, in tissue, the ever-present water condensation poses a risk of a water drop falling on the sheet and causing an area of weakness. In film, it may be gels hitting a slitter blade. Before we summarize, let's at least mention two important topics. The first is that these break initiation sites are not the cause. They are merely an important factor of many in this web break system. Other factors are nominal material properties and machine parameters. Second, we reinforce the essential concept that these events are statistically rare even if they occur regularly through the day. The reason has to do with the fraction of material involved in the defect or break versus the fraction of material that was untroubled. This means that you need to have astronomically large sample sizes for discrete measurement or perhaps continuous measurement or inspection. As we will see in the next clip, lab measurements are almost certainly not going to cut it. Splice breaks present an extra special challenge to the troubleshooter. The list of factors as to why the break favors a splice is large, and most are unique to a splice break and would not be a factor for steady-state breaks. Yes, material properties matter, as always. However, the stress concentration at a change of cross-section means the splice will be notably weaker, even if there were no material flaw and even if the splices were made perfectly. That is just the way physics are. However, as we should expect, splices are far from perfect. Also, the upsets caused by the machine during this transient are numerous and often brutal compared with steady state. Finally, splices present an almost insurmountable political challenge if the breaks occurred at your customer. You can see why by looking at this list. Every single item except nominal material properties is owned by the customer. The only option you have is to change the entire material to get this flawed area to pass through a flawed machine. I had just had a client bemoan this very situation. My best advice to him was to find a different project to work on. Rare events, such as web breaks, require a much different level of effort to make any headway compared to almost any other waste and delay issue. Every event should trigger an accident investigation. Every event should trigger an autopsy. Every event should trigger a report with standardized data fields. Thank you so very much for allowing me to share some troubleshooting techniques for rare events, such as web breaks. Stay tuned for the next clip where we will take a deeper dive into data collection and theory. Please be sure to like and share if you found this interesting or useful. See you next time.